Okay, time's come for us to spark up our host. Now, if we take a look at my topology, 9K1 is connected to VPC5 and 9K2 is connected to VPC6 on Ethernet 1.3. So what I'm going to do is I'm going to go ahead and make certain that those interfaces are configured and ready to receive traffic. So I'm going to say Ethernet 1.3, I'm going to say switch port mode access, switch port access VLAN 100, and no shut. Come over here, do the exact same thing to leaf 102. Interface E13, switch port mode access, switch port access VLAN 100, no shut, end. Now what I'm going to do is I'm going to go ahead and fire up these hosts. So I'm just going to click on them and that'll force them to open up sessions. Now I could use routers to generate the traffic, but these take so much fewer resources and they work more like PCs. These are virtual PCs that we have inside of EVNG. So what I'm going to do first of all is I want to give them some names. So I'll say set PC name. I forgot the syntax. So it's going to be set PC name. Yeah. Set PC name. I'll say host 1. And then all I'll do is I'm going to give it an IP address. So it's going to be IP address 192.168.100. We'll go ahead and say 201.255.255.255.0. It's going to check for duplicate addresses. Doesn't find any. So if I do show IP, I have my IP addresses and I should be good to go. Let's go ahead and do the other side. So I'm going to say set PC name, call it host 2. I'm going to set the IP address for 192.168.100.202.255.255.255.0. See if it takes that address. And let me see if I can ping myself, 192.168.100.202. And I can. And all I'm going to do is I'm going to go to host 1 and see if I can ping host 2. So that traffic should travel from PC5 all the way down to 9K1. And if all goes well, it should go across. So I'm going to ping 192.168.100.202 and let's see if our pings work. And they do. So in this particular scenario, what we see is our information, we have reachability from our individual hosts. So if I do a trace route to 192.168.100.202, so trace, is it trace route? I think it might be just trace. Trace it is. 192.168.100.202. What we'll see here is we are layer 2 adjacent. So destination port unreachable, code 3. So let's see, ping just one more time just to make sure it is working. And it is. Alright, so I didn't get the timeout message coming back from the config. So with this being said and with this being done, we have a fully functional environment that's going to allow us to be able to ping across and have everything actually work the way I want it to. Now what I'm going to do is I'm going to, in the next video, I'm going to shut down the NVEs. I'm going to demonstrate that this is not going to continue to operate. And then what we're going to do is we're going to explore the control plane mechanism that's actually operating inside of our multi-destination IP layer 3 transport underlay. So I'll see you guys in that video, but like I said, easy enough, easy peasy. We have a fully functional environment. Traffic is traveling from the host. In fact, let's go ahead and illustrate it. So I have host 1 that needs to talk to host 2. I gave them IP addresses of 192.168.100.201 and we gave it 192.168.100.202. They're all /24s. This device is actually connected to the leaf. This device is connected to the other leaf, 101 and 102. Now, what we did is we actually created a packet, sent that packet to the leaf. That packet, because it's arriving on an interface that's going to be in access mode, it recognizes the fact that it's going to be in VLAN 10. since it is actually in VLAN 10, what ends up happening is it gets passed to the NVE interface, NVE1. And then what's going to happen is that VLAN, that original frame, is then getting taken, and then what it's doing is it's actually getting re-encapsulated into a VXLAN header, and that VXLAN header is going to have its own source and its own destination addresses, and these are going to be the VTEP of 101, and the destination is also going to be the VTEP of 102. And then what ends up happening is that in turn gets sent from the NVE via the tunnel to the corresponding NVE on leaf 102, NVE1, and then what ends up happening is that traffic gets encapsulated and then ultimately sent to where it needs to go. Now bear in mind that we still have everything that we talked about before. All of the layer 2 stuff. Remember we talked about broadcasts, unknown unicast, and multicast traffic. Well, that traffic is actually going to be placed inside of that 239999 so that it can actually be multicast, transmitted, flooded, if you'll excuse the term, to all of the resources that need to possibly receive this information. This is going to include things like ARP. It's going to include things like, say, DHCP. Any of our layer 2 broadcast stuff. It's also going to include any of the multicast traffic that we're going to be dealing with, or broadcast traffic. So just keep in mind that this broadcast, unknown unicast, and multicast traffic in a flooded and alerted environment is going to be constrained to the multicast configuration that's going to be extending between the NVEs that are going to be providing encapsulation and de-encapsulation services for these tunnels. So again, what I want to do next is I want to dive in and shut down these NVEs, demonstrate that we don't have reachability anymore, and then what I want to do is I want to climb inside of this underlay, and I want to look at it step by step, methodically, so that we can understand exactly what's happening. And that means what we need to revisit this idea of the Anycast RP configuration and its underlying functioning mechanisms. It's going to steal a page right out of any source multicast sparse mode configuration, and we're going to see how it plays out, or we're going to see how things are going to work. It's also important to note that, remember, these tunnels actually leverage the capability of equal cost multipathing inside of the infrastructure. Now we need to keep in mind that our resources do things based on flows. So when I define a flow, for the longest time I always used the definition of a quadrant, a source IP and port and a destination IP and port. Well, inside of here we're going to be talking about something called a 5-tuple. A 5-tuple is a way a TCP IP session actually determines or constitutes a flow. And the way that's going to work is it's going to be a combination of a source IP and a source port. It's going to be a destination IP and a destination port in concert with the protocol. So the quadrant in concert with the protocol produces the 5-tuple. And we're going to use this because whenever we start looking at using equal cost multipathing, we equal cost based on hashing this tuple. So if I want to treat traffic flows separately, I need to have a way of being able to mix up the 5-tuple. So we'll look at that again when we climb in and we look at the underlying mechanism. What's happening underwater inside of this configuration is going to be kind of as simple as shutting off those NVEs, determining whether or not we have reachability from the hosts. And when we see that we don't, I'm going to bring it up step by step, and we're going to walk through this entire process. First, we'll walk through it from a theoretical perspective on the light board, and then we'll see it actually work through the use of Wireshark in our EVE NG environment. I'm Terry Vinson, and I'll see you guys in the next video.